out to come up with what's the industry ecosystem strategy for next generation memories, what we've now called 3D XPoint. At the time, that's not what we were calling it. But I was working on this thing, and
Thank you.
it was actually in a conversation with Ken. Ken and I were discussing, and there was talks about, should we form a new organization? Do we go into an existing organization, et cetera? And it was during those conversations is when, at least for me, it was the first time we actually discussed SNIA and the possibilities of SNIA. SNIA's ongoing success with things like storage management. So at least in my final recommendation that we bring this technology to SNIA, Ken was probably the most influential person that I was working with to that end. So anyway, Ken Gibson is going to now talk about that memory is the new storage. And where Rick Colson, brought down and went through the stack and basically showed how the stack is ultimately a limiter on how fast you could make storage work with this new technology. And he hinted and alluded to the fact that reducing that stack. I think Ken is going to talk about eliminating that stack. So anyway, Ken Gibson.
Thanks, Jim. So how's my sound? Good. All right. So as Jim said, Ken Gibson and I lead a team of architects at Intel focused on the software architecture for next generation non-volatile memory, and especially persistent memory. And so I think some of you know some of the stars on that team. It includes people like Paul von Baeren, who has co-chaired the programming model twig since its inception, and Andy Rudolph over here, who's been one of the thought leaders in creating that SNIA NVM programming model. So I want to pick up where Rick Colson left off this morning, and I want to look at some of the larger server and storage and data center architecture implications of the shift to persistent memory. I want to talk about the end state that we see that ending up at, which is an architecture where memory becomes the new performance storage tier. And then I want to specifically dig into the opportunities for software innovators as that software stack adapts to this whole new persistent memory-based architecture. So I want to pick up with a slide that Rick finished with, where he was showing the latency from the application down to the actual persistent media itself, and showing how, as we go from NAND today, where it's sort of 50-50 between the media itself and all the overhead in the I/O path, down to technology like 3D XPoint, where we're getting down to microsecond latencies, where the I/O steps in the software dominate the latency in that path. So Rick implies an end state where part of the answer is just get rid of the software, problem solved. Of course, in reality, I think we all know it's not that simple. You still have to manage the layout of the data on the persistent media. You still have to keep it consistent across power cycles. So you need a lot of the functionality that you get from a file system today. But also in the real world, most data stored on a server has a variety of SLAs that it has to meet for things like security, availability, cost and capacity. So in the real world, you need a variety of functionality in the path to do things like replication, snapshot, virus scan, audit trail, data deduplication. There's a whole range of functionality that has to remain there in the real world. And so I'll come back to that in a minute. But of course, the other implication of Rick's slide is, by moving to persistent memory, mapping the media right into the application's address space, you can eliminate that I/O operation. And that takes us a big step towards this end goal of a microsecond latency from the application to the media. And That's not an entirely new concept in the software world. I mean, this is a trend that started several years ago for applications that have very tight latency constraints for their access to data. So this is the trend to in-memory databases, real-time analytics applications like Hadoop Spark, the in-memory NoSQL key value services that are common in the cloud today, and also in HPC, this is common. Get everything in data and in memory to avoid the overhead of I/O operations. So now with that trend, and then now the emerging persistent memory technologies bringing high capacities and persistence, we see those merging into an architecture where the working data in dynamic memory and that performance storage tier can merge into a tier that I'm calling the in-place working storage tier. So this builds on these trends by in-memory databases where to meet their latency SLAs, they are avoiding the I/O operation with its both latency and variable latency by keeping the data in memory. So then technologies like 3D XPoint come along and they dramatically increase the capacity of memory that you have, but also create the ability to make it the persistent, reliable store for that data. So it can become the primary location for that hot working set data. The capacity storage, of course, still exists. It's probably a mix of NVM and spinning Rust. But the key decision for application developers is for which data can it tolerate the overhead of doing an I/O operation, and everything else stays in memory. And so this drives a shift away from the programming model that we all learned in about the second week of our first introductory programming class. And that was the programming model where you allocate memory and dynamic in DRAM, operate it there, and then open a file and do file reads and writes to persist the data. We don't really think of it as a programming model because it's just so ingrained in how we write software today, but it is a programming model, and a programming model where in the twig we've created the alternative where you allocate data one place, you operate it on it there, and it's persisted there. And that's why we call it a programming model twig. It is an alternative programming model that you can use on top of persistent memory. So the question is, so we've got applications using this programming model. We've got DIMMs mapped into the application's address space. We're going to hear later today from a couple of the leading OS vendors what they're doing to create the OS infrastructure for that. We heard a preview from Neil Christensen at the SNIA Developers Conference last September on what Microsoft is doing with Windows. In the open source community, you can see what Linux is doing, and I think we'll hear about that this afternoon. But the question is, what about everything else in the middle, in a real-world stack? So today, this is one example of a real-world, street-legal server storage stack. So it's got the separation of working memory from block I/O-based storage. It's got the file system. It's got the block drivers. And it has this functionality that almost always exists for meeting the variety of SLAs that real-world server data has to meet. I'm showing it here in the software stack. There's been a trend for many years to move it out to SAN and NAS devices. Today, with the trend to hyperconvergence and low latency NVM, I think that's going to drive a trend back into the host stack like I'm showing it here. But the key is, some or all of this functionality almost always exists in that stack. And it's things like replication and snapshot, tiering and caching layers, audit trail, virus scan, It's a variety of these things in a real-world stack. So, step one today is doing some things to tune this up a little bit down here. So, Rick talked about NVM Express and attaching the NVM right to PCIe. For today's NVDIMMs, we're seeing optimal block drivers that create a block I/O abstraction on top of load store memory. I think you can see some of that going on in the Linux open source. There's work happening there. But it's still a long way from that end state of true microsecond access from the application down to the persistent media. So how do we evolve this to that future state of in-place working performance storage? And now that I have you on the edge of your seat, I'll tell you, I don't have the answer, but but I'm going to propose some steps forward to help stimulate thinking in this space. So what's a possible step forward? So the NVM programming model and persistent memory in a DIMM mapped into the application's address space is about exposing that right to the application, versus behind a kernel-based stack, as has always been done for decades. So that creates the opportunity as a next step to start moving this functionality into a user space library. So you get the advantage of load store access underneath. You get the advantage of direct load store access from the application while using libraries to bring some of this functionality underneath familiar file-based APIs that maintain the separation of working memory and persistent media. So with that separation, you retain that data move and that ability to insert functionality in that data path as you're doing that simulated I/O between your working memory and your persistent memory. That key operation that for decades has been used by suppliers of these data services to insert their functionality into the data path, between working memory and persistent storage. So this is one general path forward towards that end state of in-place working storage is functionality that can be hooked in underneath the existing programming model, the existing file I/O-based programming model from the application level, but then using this direct mapping ability of the NVM programming model and persistent memory DIMMs underneath. So this could be a stepping stone towards getting to the end state of true in-place working storage. That I/O and that I/O intercept point that has been used for decades goes away. It's gone. And replaced with new and improved APIs and data services. Simple, right? So again, I don't have the answer, but I do want to talk about what we're doing at Intel to at least kickstart some of this innovation. And what we're doing is an open source project to develop a set of what we call NVM software libraries. It's really a collection of libraries. We call it NVML. It's fully open source. It's here. You can go look at it at pmem.io. And what we're doing here is we're starting with the basic foundational level functionality that applications typically would want to use in order to interact directly with a persistent media. So at a basic level, it includes the option to use the non-volatile DIMMs as just high-capacity volatile memory. And that's what the That's what the V is in these functions, is just using it as a high-capacity volatile memory and using the familiar APIs to malloc and free chunks of memory. It also adds in libpmem some of the functionality and the basic mechanics that you want to have to start using the DIMM as a persistent media. So earlier this morning, Rick just very briefly showed a picture of places where data can get held in a typical architecture. You know, writes to memory go through various levels of internal processor cache. There's an I/O controller, you know, that can cache data on its way out to the DIMM. And so pmem includes some basic functionality for pushing that data out to ensure that it's stored on the persistent media. And then on that, we build a set of functionality that today application developers get in file systems and various levels of the I/O stack. And that's functionality for making sure that collections of data, transactions are either all committed to the persistent media, or in the case of a power fail or an unexpected program crash, they get fully committed or rolled back on a program restart. Again, stuff that file systems handle, layers of the I/O path handle. So application developers don't typically have to think about it, and so this gives them some functionality, so they still don't really have to think too much about it. You know, the library handles it for the application for direct mapped persistent memory DIMMs. So the start of the basic functionality, and as an open source project, we have a mix of future experimental ideas, you know, early access to some untested code, and everything from that down to a core set of functionality here that's been pretty well tested and we think is suitable for, you know, OSs to take and start, you know, bundling with their OS distributions. So one of the concepts that the library introduces is this concept of a persist point. So again, a program, you know, writes a byte of data out to memory. It may get cached in internal processor caches. It may take a while to push through the internal I/O controller. So the persist point is when an application has completed some significant update to its memory. It could be a data structure representing a transaction, you know, for example, an airline, a travel reservation, whatever the transaction, you know, is. So we introduced an API for doing a persist point so the application can now reliably persist that updated transaction in its data set, you know, in its in-place working storage. So yeah, again, at the base level, it takes care of the functionality of pushing the data out. But from an application level, it's the point where the application has done something significant to make a incremental change to its persistent data set. So that's the logical place where a middleware layer might likely want to intercept that call to do something like snapshot the data, check for data deduplications, kick off a replication to you know, somewhere else, or tiering back to the capacity layer, or some of the functionality that today is done by, you know, hooking that call chain in the I/O path. So it's important to understand that this is not a guaranteed control point between the data and the persisted media. It's still memory. It's still load store accessible by the application. But it does create an initial beachhead for thinking about how do we apply these necessary data services and functionality in a new world of persistent memory-based, in-place working data. And again, it's all open source, and the innovation is happening in the open, out at the open source website. So you can join in. Again, everything's happening in the open as open source. We've got a collection of resources here to get ramped up, including the NVM Programming Model twig that we and several others here, like Microsoft, Red Hat, VMware, and many others, are participating in extending the programming model, extending the specs. So join the conversation. And I think with that, I have time for a couple of questions. Yes?
Thank you. It's a great talk, and thank you for doing this in open source. The previous couple of times that the industry worked on things like this, we built it at Tandem first, and then Fusion IO did a little bit of similar work on comics. I find your ideas on the last couple of slides quite intriguing, which is what you're doing versus write-ahead logging, which was the primary mechanism to trigger replication and all. It's quite interesting you're doing something different there. And then your other allusion to no page caches. So I wonder if you could expand on those two thoughts a little bit more. What's triggering this change of things?
Well, I mean, of course, the base change is the mapping of persistent media right to the application, something typical application developers aren't used to dealing with. And extending the trend to in-memory databases using DRAM as a local cache of their working data set, helping them take the next step to that's also the primary reliable version of the data versus effectively caching your data while still needing to do IOs to get updates pushed back to reliable storage through an IO-based model. So I think that's the best answer I have to your question. So yeah, question here. Moving across.
Any benchmarks for other DAX-enabled file systems other than ext4?
No, we don't.
Would you be?
Do we have any?
Other than ext4, would you be doing it for?
We will, but those benchmarks really ought to come from the suppliers of those, those file systems, and I think we'll hear from at least one of them this afternoon. Yeah, there was one here first. Go ahead.
So real quick, so it seems like given all these different SLA requirements and human error, possibility of human error, it seems like a single level store is not the way to go, correct?
So I think you're raising a good point that by mapping the persistent. Oh, so the question was, if I can paraphrase, I think the question was you're concerned about human and programmer errors when you've got the media mapped directly into the application, right? And that's a good point. And so we are shifting. Mapping the persistent media right to the application definitely shifts more responsibility to the application developer. So if you're storing data that you care about, you want to trust the application that it's tested at a level where you can trust what it's going to do with that media. And question here was next.
So as time goes on, we might expect that memory controllers might more natively match what these new next generation memories look like. Do you anticipate that these libraries will persist over time being an extraction mechanism in order to extract those hardware differences out?
Yes, I do. And so the question was, as hardware evolves, do we expect these libraries to maintain a consistent set of programming APIs for applications, right? That was the question. And yes, absolutely, that's one of our goals. Is that we're Intel, the hardware company, but again, we're trying to kickstart the innovation amongst the software ecosystem to build that set of software APIs, and that is exactly one of our goals with these libraries. And yeah, question there.
So since right now we are trying to propose a new programming model or programming paradigms to leverage these persistent memory, but so they could have a concern on the software industry because they already have lots of legacy code. So what's your strategy to convince the software industry to adopt this kind of new concept
Good question. So the question was, summarizing is, what's the motivation for application developers to learn a whole new programming model? Because you're right, that's a significant concern. And I think the answer is two things. One is go back to the latency picture. So it's the benefit for performance improvement and dramatic improvement in latency. And then two, the intermediate step that I proposed a few slides ago, where you retain the I/O model and existing file-based APIs, does give you a certain benefit to use direct map persistent memory while transparently maintaining the existing file APIs for most applications. So I think that's, that would be the ideal path forward here into this future. Yeah, I think over there we had a question.
So it seems like you, like I mentioned before, if you're using these new memories with PCIe, or even with the DIMM that has a lot of limitations, is Intel planning a new bus standard or new CPU?
I can't comment. I'm the software architecture manager, so I'll just leave it at that.
Let's see what the question was.
So the question is, are we planning new buses, new interconnects for new types of NVM? And I think the answer is, today we're going memory attached and PCIe. I mean, that's our plans. Yeah, I think back there you had the next question.
How does this model expand to share data that needs to be shared among multiple server systems, or does it not?
So I think I see an industry quickly. What I see is the trend towards moving towards direct attached NVM, which then puts pressure on the fabric and the network. So what I'm seeing is a combination of improvements in fabric and network technology combined with software layers for bringing that replication and global namespace across a cloud-like architecture. One more. I think I'm allowed to have. Yeah, we had one right here.
May you go back one slide?
Yeah.
The female I/O slide. In this diagram, what entity in the system that manage the partitioning on the MVD in the bottom, the MMU mappings, and how does the multiple applications interact with that MMU mapping things in order to access to the MVD? Because typically they go through the file system to do the memory allocation, the allocation, etc. Does that all provide facility so that they can dynamically change the partitioning, the sizes, etc.?
Yeah, so the question was how do multiple applications deal with partitioning and sharing DIMMs?
And the partitioning on the bottom, are they growing dynamically, changing back and forth depending on application requirements, or they are fixed after you partition?
Yeah, so the short answer is we're moving to the memory model, the virtual memory model, and the protected memory that's been in the Intel architecture for decades, combined with some of the extensions to the BIOS level interface to the DIMMs that have been spec'd through the ASWG working group around detecting and partitioning up DIMMs at the platform level. So it's a combination of those two. Then just third step is an aspect of the SNIA programming model is the ability to use the file system for managing partitioning of this media. So you can open files, apply the familiar file-based protection model, but then let the file system get out of the way once an application has opened a region of persistent memory and then mapped it into its address space. So that is a core aspect.
On the diagram, that is effectively a small file system that they can also do the memory allocation, the allocation.
Yes, and this is a core aspect of the SNIA NVM programming model that we and others have created in the twig.
Thanks, Ken.
Okay, thank you.
Okay, so with that, it's a 15-minute break now. I'd like to remind people that there's demos out there for that the NVDIMM SIG has put together. I recommend that you go and visit the companies that have come and provided those demos. And we'll see you in 15 minutes. We have Tom Coughlin and Jim Handy coming up next.